So for today's class, we're going to deal with the fundamental concept of AC circuits. So before going to talk what is mean by AC supply or AC circuit, so we need to understand the term what is DC current or DC circuit, DC supply you can say, and what is the AC supply. If you try to recall your previous lectures in which we have discussed what is DC supply and AC supply here. So definition for DC supply or DC current. So here your voltage or current does not change with respect to time with respect to time. So if you draw the diagram for this, so this could be coming like this. So this is my time, and this may be a voltage or current magnitude can be shown on the y-axis. Then this is the straight line constant value you are getting. So irrespective of my time is varying in this direction. For each time instant my voltage or current is always a constant value, so that is the DC supply of characteristics. And come to that AC supply or AC current. So here the magnitude of the voltage or current quantity changes with respect to time. So that is the definition if you talk about what is meant by alternating current or alternating supply systems. So here you can take example for that voltage or current quantity, and here I am taking the alternating waveform is a sinusoidal waveform taking, and this is a with respect to time. If you notice this sinusoidal waveform, so this is has zero amplitude at the zero time, and it has the maximum amplitude at some time t1, and some time t2 again 0, at the some time t3 again this has the maximum negative amplitude. So like this it is varying from it is varying in this direction as on my current is varying. My current is increasing, so sorry, my time is varying, so my current amplitude is varying accordingly the time changes. So that is what the definition you need to understand what is mean by this AC supply. So in the earlier days the power invented, that is nothing but a DC only, isn't it? It is a DC supply. The early very initial days, whatever the electrical power that is deal with the scientist, that is the DC power, and that is invented by the this is DC power only. So in earlier days we also know that in earlier days the generation of DC power and the utilization of this DC power both has been happening at the same place, where here there is no need to transmit the power. So whatever you are generating is power, the DC power from your place, there itself we are going to utilizing that DC power to has become a load. So that was the concept, that was the phenomenon which has been done at the earlier stage. When the AC supply when the AC supply was later on developed, and along with this AC supply development, so here due to due to increasing of increasing of power demand power demand, so we need to transfer power to the longer distance, power to the longer distance. So what is the meaning of this? How need to transfer the power to the longer distance is that, suppose you know, the coal is one of the fossil fuel which is responsible to produce the electricity. So whatever the AC electricity we are producing from that thermal stations, the mainly we are going to use that coal as a fuel there, and coal is a fossil fuel we are going to use there. So and these coals, if you talk in Indian scenario, these coal mines are mostly are available in Odisha and Bihar, Bihar, Telangana, Telangana. So these are the main states which are producing the major coal fuels to generate this power. So these are the places we have. But whatever the coal production, you cannot transmit this coal to a longer distance, because that there will be a incurring of the transportation charges. Therefore some thermal plants which are established, thermal plants are established where the coals has been available at the nearest places. That is the okay, that's fine. But my actual load demand will be more, will be required for me is more, is like the cities like Hyderabad, Delhi, Bangalore, Chennai, and Mumbai. So these are the major cities we know we have, and my power plants, whatever the power plants which are far away from this major load, isn't it? Major load. My loads are far away from these generating stations, because these generating stations which are you can construct at near to the coal mines. So it is like NTPC of Ramagundam. There you can see that coal mines are mostly available, so you can extract the coal from there, you can utilize the same thing. But my actual power has to be transferred, that Ramagundam NTPC, that power to the rest of the country, in like what is something like how to transfer that to Hyderabad, Delhi, Bangalore, something like. So there is, we need a longer distance transmission. We need a longer distance transmission. So longer distance transmission is required. So to do this longer distance transmission also, the AC is mostly preferable. AC supply is mostly or most economical. So that is the point I want to talk here. So even though in the late 1960s, there is a whose argument has been gone between the DC people versus the AC people, and they wanted to stress many points. So which supply we have to use, whether we will go for the DC supply or whether we go for the AC supply. So those kind of so many arguments, so many conflict has been arised, and finally they have been gone with some conclusions here. So we'll see what are the drawbacks of the DC, so that we can come to know the advantage, why we are prefer to go for the AC system. So drawback of DC supply. DC supply. The first point we need to discuss here is to differentiate which supply system is best. So I can write DC power cannot preferred for longer distance, so that is the point, due to more losses. So this is what is the point you need to understand here. Suppose I have a DC supply and this is my transmission line, and this is my load point is there, something like this, load point is there. So here DC supply and this is my transmission line here. So obviously this transmission line has some resistance R. This is my load here, you can take this is VL. So whenever the current DC current is flowing through this element here, the DC current is flowing through this element, some DC current is flowing through this element, there is a drop here, that is I into R drop is there. This is called there is a drop is there, as well as there is a power loss, that is called I square R loss. I square R loss can be happen here. So if my I square R losses are more in case of DC system, therefore more losses could be occurring in the transmission line. Obviously at the receiving end, at the load end, you will get very lesser amount of power. At the load end you are going to get the very less amount of power. So that is the one disadvantage of DC circuit, you cannot prefer for longer distance. If suppose I just want to tell one more point here. If for longer distance, if you use a longer transmission line here, then you know one another relation here, R is equal to rho L by A. A is cross section area of the conductor, rho and L is also there. Suppose you want to reduce the I square R losses. Suppose you want to reduce the I square R losses, what could be you can do here? So I want to reduce this resistor here so that I can reduce this loss. So if you want to reduce this R, obviously you have to reduce this R, obviously you have to increase the cross sectional area of the conductor. So if you increase the cross sectional area of the conductor, the size of the conductor will going to increase. Size of the conductor will increase, therefore it is not economically feasible, the cost of the conductor will increases. So similarly if you want to increase or decrease this resistivity, so this resistivity also is different for different materials. We have a gold is a conductor, that resistivity is different, and if you go for that silver material, their resistivity is different. So there you also, the gold as a conductor or silver as a conductor also we cannot encourageable, because those are the very costly affairs. Therefore again I just want to tell one more thing here. So I also know the power it can be written as it is V into I. So this is the equation we also know for us, isn't it? So in order to decrease these losses, decrease these losses in case of this DC supply, if you try to decrease this ice current, if you try to decrease this current also, you can able to decrease the losses. That is also one of the feasibility is there. Suppose if you want to decrease this current here, if you want to decrease this current, you need to increase this voltage to maintain the power carrying through the circuit should be a constant, to carrying the circuit to be constant. So increasing the voltage level may not be this provision is not available in the DC supply. Increasing of voltage levels, this is not feasible or not applicable for the DC systems. because this can be done in case of AC system. The voltage levels, the voltage level, or we can step up the voltage, we can increase the voltage or step up the voltage, in case of AC system, AC system, so that losses can be minimized, losses can be minimized. So this is can be losses can be minimized. How will going to increase the voltage or step up the voltage, step down the voltage? Because in the AC supply you are going to use the transformers. So these transformers are available in AC supply. There you can increase or decrease the voltage level, so that you can try to decrease the losses in a transmission line, if the line which is going for a longer distance. This provision is not be there in the DC supply system. So for DC supply system cannot be is preferable for longer distance, because it is going to create more transmission losses. So that is the point I want to discuss here. The third point is that for third point I want to tell you here is this. Here is the most of the electrical drives uses AC motors. AC motors. Let me to tell you why can't we go for the DC motors? Because DC motors have these DC motors have commutator. These commutators are called converters, so which are responsible to convert your DC into AC, so that your DC motors will rotate. So and moreover, the disadvantage of the DC motors is they produce the heat and have the maintenance cost. The maintenance cost is also matters here. So that's why you cannot encourage DC motors. If you encourage the DC motor, obviously you need to go with the DC supply. So we are not going with the DC supply, so therefore we cannot even you cannot encourage the DC motors. So for our household applications, as well as for agricultural applications, mostly we are using this induction motors. Induction motors, or you can call the AC motors. So AC motors we are using. So in our household applications, in agricultural pumping, water pumping motors, or industrial applications, we are mostly going with that AC motors. The advantage of this AC motors, which are more rugged, robust, which are more robust, and they are and economically cheaper. You can say economically cheaper in cost. So that is the another advantage of the AC system utilizing, and drawback of your DC supply system. The next drawback of this DC supply is, if you use the DC supply, this is going to problematic for your switch gears. This will going to problematic. Switch gears comes going to be a problematic, you can say problematic. So what is mean by this is, suppose I have a switch something like this. So this is my switch, it is my something load is there, and this is my DC current is coming like this. So whenever I suddenly open this switch, so as you know that the sudden change in the circuit, thus cannot be happen. So sudden change that cannot be taken by any kind of circuit. So therefore if you suddenly open this switch, therefore there is a arc will be formed between these two gaps. This arc has going to be formed here, and if this arc is not extinguished, therefore it is going to produce the heat, and therefore it is leads to damage the equipment. This is going to damage the equipment. So that is was the consequences if you use the DC supply, and if you suddenly open the switch gear point. So for the sudden change, sudden opening or sudden change in the circuit, so there is in between these two contacts, so this is going to form a arc, and it will dissipate the heat, and equipment damage can be occurs. But this is not the case in case of you go with the AC system, because for AC system, so this is my alternating current is coming like this. So this is my alternating current. So this alternating current has varying maximum going and coming to 0 as well as negative point. So therefore for suppose it is a 50 hertz sinusoidal signal, so it is around it has a 100 points coming into 0 for a 50 hertz cycle. So 100 points are coming into a 0 position for a 50 hertz cycle. So I can say that, so if my switch is very efficient, then can easily open, and this arc extinguishing can be done easily if you use the AC system. So this concept anyhow you will going to learn in case of switch gear and protection very detailed what is meant by this, and what could be the advantage of AC system as compared to DC system. Those concept you can be go to the detail. So these are the 4-5 points I want to stress here to understand the importance of AC supply system. So DC supply system drawbacks is going to be advantageous to the your AC system, and it is mostly preferable. So due to these reasons, we are going with this alternating current quantities. So due to these reasons, we have opting to go with that AC systems, isn't it? AC systems has major advantages as compared to your DC system. That's why we are going with this alternating current system. If you want to talk what are the alternating current waveforms we have available for our electrical terminology, if you talk, so different alternating current quantities are available to us. If you talk, it is a sinusoidal waveform, or it is also alternating current, or it is a triangle waveform, or you can say it is something like the trapezoidal waveform. So all these are the alternating currents only. Alternating currents. So you can talk something like this. Yeah. Okay. So if you talk what is this sinusoidal waveform, mathematically how to write this one is nothing but V is equal to it can be written as Vm sin omega t, where this is called a instantaneous value, and this is called the maximum value or peak value, and this is the time here, and this is called the angular velocity of the coil, angular velocity of the coil. So what are the definition of instantaneous value, maximum peak value, that will going to cover in the coming topics. So that will going to do in these things. So what I try to stress one point here is reference here is, so we mostly prefer among all these different waveforms, sinusoidal waveform, trapezoidal waveform, and square waveform or sawtooth waveform, different waveforms we have, but we mostly prefer, or we preferred sinusoidal waveform. we prefer a sinusoidal waveform as a alternating current waveform. So that is what we are going to use. So let me to see what are the advantages, why we are going to use this sinusoidal signal only as our alternating waveform instead of going with the triangular wave and going with the trapezoidal wave. Why we are not going with these two waveform, why we are going only with the AC waveform. So that is point we need to understand. So first point what I observed from this merit is, so why we are going for this sinusoidal signal is, the sinusoidal signal is easy to generate and transmit. You can sinusoidal signal you can easily generate and transmit. So that can be done. The second point is the derivation of derivation or a integral of sinusoidal signal is sinusoidal signal is sinusoidal. That is the another advantage. What is meant by this is, as we know that in case of your AC quantities, we are going to use R, L and C. If you write what is the expression for current in terms of R here, you can write some V by R. What is the expression of current for this in terms of inductance, then also you know the expression 1 by L integration of some V into some d of t. If you write what is the expression for current in terms of capacitance, then this is going to give C dV by so dt. So these are the different expressions we have here. Here it is the, if you want to get the current here in case of inductor, so it is the integration of voltage. If you do, then you will going to get the current in the inductor. In case of current find in the capacitor, this is the differentiation of this voltage. If you do that, then you will going to get the current. So that is the concept. I think you might be known from your previous class as well. So here if you want to see some kind of things here, suppose my voltage waveform is sinusoidal. If my voltage waveform is sinusoidal, and if the same current if you want to find for R resistance, then also my current waveform also sinusoidal, isn't it? If you do this R resistance, so this is also we are getting sinusoidal, IR, IL and IC, you can say something like this. So this is my current waveform, this is the voltage. Again, if you want to find what is IL, for IL also if you do the derivation of voltage, so if you do the integration of voltage, so integration of V, what is V here? V is nothing but what here? V is nothing but Vm sin omega t, you know. So integration of this value, if you do this one, so what we will going to get here? 1 by L. So this is what Vm sin omega t dt. Again it is going to give us minus some Vm by L some omega into some cos omega t, some kind of thing it is going to give us. It means your IL also coming in terms of sinusoidal signal. So cos omega t can be converted into sin omega t. You can write if it is a sin omega t plus 90 degrees. So if you write the plus or minus 90 degrees, you can easily convert this cos omega t into sin omega t. It means that if you use the sinusoidal voltage signal, the current is also coming sinusoidal, and my inductor current also coming sinusoidal, and similarly if you do for this one also, this is for IL, and for this one also if you do the derivation of this sin omega t, the d by dt of sin omega t, again you will get the sin omega t, isn't it? So it means IC also getting the sinusoidal signal. For IC also you are getting the sinusoidal signal. So if you see here, voltage waveform is sinusoidal signal, my IR, IL and IC, it means the current quantity is also sinusoidal signal, which is we are getting. So that is why we were going to use, that's why we are going to use the sinusoidal as mostly preferable. So that is what I want to talk here. So suppose instead of this sinusoidal signal, if I use trapezoidal form, if I use the trapezoidal voltage, something like this, then what could be the my current? Of course my current IR may be same, of course my current IR may be trapezoidal point, I can take IR is trapezoidal, but when it comes to my IL, the IC, the differentiation of these two, if you do the differentiation of IC, then this is not a trapezoidal, this coming something like a triangular wave, something like this it will come. So this is what the IC, this is what the differentiation we are getting, differentiation. Now see here, or similarly if you do that integration, then IL also some kind of another kind of shape you are going to get. So there is no uniformity between your voltage waveform, current waveforms of IR, IC and other things. So similarly this is the case also for your triangular waveform also. There also the integration waveform is different and differentiation waveform coming different. So you cannot prefer this triangular wave, trapezoidal wave, but we will prefer sinusoidal wave, is because for derivation, if integration if you do also, you are going to get the same sinusoidal signal. So that is the reason why we are going to use the sinusoidal signal. That is the second point of this one. The third point is, so the Fourier analysis can be done very easily. Fourier analysis can be done easily. So if you want to do the analysis, spectral analysis of the signal, so you need to go for the Fourier analysis. So this Fourier analysis is very easily you can do if your signals are in sinusoidal. So that is what the point. The next point is, if you use this sinusoidal signal, then it is going to produce a less iron losses. So this is the another point we need to understand. So iron losses are is nothing but it is a combination hysteresis losses and eddy current losses is there. So your hysteresis are directly proportional to frequency and your eddy current loss is directly proportional to the square of the frequency. If you use the sine wave, only fundamental frequency is available. If you use the other waves, then you have a fundamental frequency plus some harmonic frequencies 3, 5, something like this. It means this frequency quantity is increasing, but it is sine wave, it is only have a fundamental frequency. So therefore if the frequency quantity increasing with the other waveform, so if it is increases, this losses also increases. If you use the other waveforms, this is the consequences can be happen if you with the other kind of waveform. But if you use the sinusoidal waveform, so only the fundamental frequency is there, so our losses can be, this iron losses can be minimized. Now let me to talk some simple terminology of sinusoidal function. Terminology of sinusoidal function. Terminology of sinusoidal function. So this is the some terms we need to define here. So as we know this, so this is my sinusoidal wave we have for any kind of quantity, it is current or voltage, we can take it is a current quantity. Then you also know, so it is can be written a maximum 2 pi is there, and this point is pi degrees 0, and this is pi by 2 it is, this is pi, and this is 3 pi by 2, 3 pi by 2, and you can take this is the maximum point also, you can say it is the I maximum point. Similarly it is also coming like minus I max point, something like this. So if you write the equation for this AC quantity, then the instantaneous current I can be written as I into Im sine omega t. So this is what I am writing here. If you take this one up to 2 pi radians, up to a 2 pi, whether your sinusoidal signal is started from 0 radian, 0 degrees, and pi by 2 pi and 3 pi by 2, and up to 2 pi point radians it is going. So up to this point I can take it is as a one cycle. So how will you define a cycle here? How will you define a cycle here? So it is a complete set of positive and negative values. You can define now complete set of positive and a negative values of AC quantity. So that is the meaning, complete set of positive and negative values. So this is the positive values and complete set, and this is the negative values. This is going to form a cycle. Generally one cycle constitute, so generally one cycle constitute 360 degrees or 2 pi radians. That is what, for one cycle you maybe have 360 degrees or 2 pi radians. Then another term we need to define here, it is called a time period. Here, time period. So I will define this first, then I will go further. The instantaneous quantity time taken to complete one cycle is called as time period. It's called as time period. So that is the definition. So let me to explain this one with the diagram here. So if it is a my AC quantity is going like this, if it is something like this there, and this is my omega t, something like this there. So for this circuit, so this is what the one complete cycle, this is what the a complete cycle, one cycle, you can say one cycle. To complete this one cycle, how much time it is taken, that is called a time period. So instantaneous quantity, time taken to complete a one cycle from this point to this point. So this is a complete one cycle, it is complete one cycle. To complete this one cycle, how much time it has been taken, so that is called a time period. It is called a time period. You can talk, suppose example, if my waveform has 50 hertz, then I can say that this has a 50 cycles per second. So that is the meaning. So one, one cycle means this is called a one cycle. So like that we have 50 cycles per second, then that is called that waveform has, for that waveform you can say that waveform is a 50 hertz frequency. And you also know the time period, this time period can be denoted with the capital T, time period T. So this time period T is inversely proportional to your frequency f. So I can write this is 1 by 50 hertz. So I can write it is going to take 0.02 seconds or 20 milliseconds. So for 50 hertz it is going to take 20 milliseconds to complete the frequency. So that is the meaning of this frequency and time period. Now we're going to see what is mean by maximum or peak value. Maximum or peak value. So that is I want to define here. So it is the highest magnitude of the alternating current. It is the highest magnitude of alternating current with respect to positive and negative, positive or a negative. So that is the meaning I want to express here. So suppose we have a waveform something like this, it is I something like omega t. So this is my waveform, isn't it? So what is the highest magnitude for this cycle, this waveform? So this is my highest magnitude in case of positive cycle, and it is the highest magnitude in case of negative cycle. So I can say the maximum peak of this waveform is this. So this is my maximum peak Im, or this is the maximum negative peak minus Im. This is plus Im, this is minus Im. So this is how the maximum or peak value can be defined. The next term is instantaneous value. Instantaneous value. So take the definition of this. The value of an AC quantity at any instant of time, is called a this is called a instantaneous value. So you can if you draw this diagram, with this you can easily explain this definition. So this is my AC quantity I have. So this is what the time with respect to time at each and every time for T1, T2 and T3, for every instant what could be my value, and that value is called the instant value of this alternating current quantity. So that is the meaning here. Every instant of time what could be the my value of alternating current, that is called the instantaneous value. Now we'll go for what is mean by this frequency here. So the frequency, how will you define this frequency here? So frequency is number of cycles occurs per second. So number of cycles occurs in 1 second is called that frequency. If in 1 second how many number of cycles is going to be going through that is called a frequency. The frequency is equal to f is given, it is inversely proportional to time period. So it can be written as 1 by t. So 1 by t, so hertz, or you can say you can be say it is cycles per second. So number of cycles per a second, that is called the frequency f, or f is directly proportional to 1 by t. So that is the definition for your frequency. Now what is this angular frequency here? Angular frequency angular frequency, so it is the radian per second, radians per second. So this is called the angular frequency, or radians per second, or it is also equal to 2 pi by t, something like this. So this is the how many number, or how many for a second, how many radians the your waveform is able to pass. So that is called a radians per second. So that is the definition. And phase angle, so phase angle is a very important term you need to understand here. So for phase angle is given as, if you have a waveform like this, if you have a waveform like this, so this is my waveform, and it is has the 2 pi, and this is pi, you can say 0 is there. So this is my complete one period, this is complete my one period. Suppose I want to find at a fraction of time t, for a some fraction of time t, I want to find what is the phase angle. At this moment I want to find what is the phase angle from this point to this point. That is what I want to find here. What is my phase angle from this point to this point. So at the fraction of time t, what could be the phase angle of for the given waveform. So that is what I want to. So thus theta, the phase angle theta can be written, how to find that one is theta is equal to the total radians into the fraction of time where you want to find the phase angle and total time period. If you do this one, you are able to find what could be the phase angle of the any waveform. So this is another concept you need to understand. The next one is phase difference. Phase difference. Phase difference. Suppose I have a waveform something like this. Suppose I have a waveform, this is a waveform, some quantity, you can say a waveform is there, and I also have the another waveform which is the starting from 0 point in somewhere here, so something like this. So this is my B waveform. Then in between your A waveform A and waveform B, there is a phase angle difference that I can write. This is the pi. Pi is a phase angle difference between your A and B waveforms, or A and B quantities. This is called the pi is a phase angle difference between A and B quantity. A and B quantity. But what about which waveform is leading and which waveform is lagging? That is what I want to say here. The first 0 instant was happened to A waveform. So it is the first waveform which is I can say the waveform A is leading and B waveform is in lagging condition. So I can write the statement here: A leads waveform B by how much angle? Pi. A leads B by a pi angle. So that is the meaning. Otherwise, you can give another statement: B lags A waveform by pi angle. So that is the these two statements are correct. A waveform is leading B waveform by a pi angle, or B waveform lags A waveform by a pi angle. So that is the meaning. A is leads by B by pi, or B lags A by pi. So that is what the phase difference and leading and lagging concept. I will take one more example here. I will take the one more example here. So this is A waveform. Again this is my B waveform. Again this is my B waveform. Here this amplitude may be different. Here amplitude may be different for both the waveform, but the phase difference is 0, isn't it? There is no phase difference. So I can write A and B are in phase. A and B are in phase, but amplitude may be different, but the phase angle is between, or phase difference between A and B signal is 0. So I can take the statement here is A and B are in phase. So that is the scenario here. If I go with another scenario, something like this, so this is some another scenario 0. So this is my waveform. I can take, this is my A waveform, and my B waveform here is start from somewhere here, something like this. So there is again there is a phase difference between these two, again phase difference between these two waveforms, A waveform and B waveform. So here also I can give the statement. How will you give the statement here? The B waveform lead A waveform by angle pi, or my A waveform lags B waveform at an angle of pi degrees. So that is what, because the first 0 instant has occurs at the B waveform, so it is leading, it is coming before the A waveform, it is coming before the A waveform. So it is leading by what angle? It is leading this B waveform, leading A waveform by some pi angle. So that is what leading and lagging and phase difference as a concept. So next concept will go is that called average value. Average value, or you can say it is the mean value. Average value, or you can say it is a mean value. You take the statement now. What is average value? So take the statement. It is defined as the steady current. Steady current means it is a DC current. It is a DC current that sends the same current, that sends the same charge through a circuit in the same time period as the AC current does in half of its time period. So this is a very lengthy statement for average value. So this is the statement has been given for to average value. So to understand this, so let us take this. It is a DC circuit. If we have something like this, so this is purely DC circuit. You can say VDC. The current also IDC is coming. So due to this current, the charge Q, is produced. Charge, that is the amount of charge Q is produced for some time t. You can say some for a given time t. So Q is the amount of charge has been produced by this DC voltage or DC circuit. But if you go for the AC system here, if AC system, so this is my VAC there, so it is R is there, so it is also produce the same amount of charge Q at that time, which is half of the time which is taken by the DC system. So that is the meaning. So same amount of charge, the same amount of charge can be produced by both the system, but time taken by this DC system and AC system is different. So it will going to take, if the time t, then half of the time it is going to take to complete the charge or work done. So that is the meaning of this. Suppose if we have a waveform something like this, if we have the waveform something like this is pi and 2 pi, so and this is time. So in half of the waveform, half of the wave or half of the time it is going to complete the work done. So it will take t time to complete this work done, to send these charges, but it will take t by 2, half of that time to work done or send these charges through this network, something like this. So this is what the understanding of this statement with diagrams. So if you want to calculate average value for sinusoidal signals, so if you find what is the average value for any signal, so this generalized form is there, it might be studied in your any classes. So average the area under the curve, by time period, so that is the formula you need to understand here. So what is the in case of this sinusoidal signal, you have to take note here, you have to take the note for symmetrical waveforms, to calculate average value, we need to take half time period, otherwise you can take the total time period. So that is the point we need to understand here. So if you want to find what is this average here, so that average you can calculate here. So I want to find, this is, if you suppose it is a voltage waveform, then I can write V average. So V average I can take the area under the curve. So for this curve, this is a sinusoidal signal, it is a symmetrical signal. So it is a symmetrical signal. For this signal I only go with the half cycle I will take, I will calculate the average of that waveform. Otherwise if you go with the full cycle, then the average of the positive cycle and negative cycle will become the 0, isn't it? So that's why you cannot go for this, for symmetrical system, full cycle of the system. So that's why we are going to consider half period of this system here. So if you take the, what is the area under this half period, so I can write this area is can be taken as 0 to pi, half period I am taking, and Vm sin omega t and dt, and by the time period. What is the time period from here to here? It is 0 to pi. So I can take it is the pi. If you simplify this equation by using your integration formulas, so this is going to get 2 pi, so it is obviously 0.6 637 into that Vm. So this is what the average value for a sinusoidal signal. Now we'll go for another terminology. It's called RMS value. It's called RMS value or root mean square value. So to understand what is RMS value and why we need this RMS value, so to understand this, so let us consider this is my DC system. So this is my DC system with simple R is there. So whatever the voltage is coming, this is plus, suppose it is 5 volts is there, and this is the resistive circuit. So it is going to dissipate the energy, or it is going to produce the heat of energy. So I can say it is producing a 1 kilocalorie, 1 kilocalorie of heat for a given time t. Some given time t, if I use the 5 volt DC supply system, then it is going to producing 1 kilocalorie of heat through this resistance. So this 5 volt DC means that is nothing but a average voltage. This is nothing but average voltage. Suppose by taking the AC system here, by taking the AC system here with the same resistance R, I want to dissipate, I want to produce the heat of 1 kilocalorie here, energy here for the same given time t, then the voltage which is required for me to produce this condition, to satisfy this condition, that is required, is called, the voltage is called Vrms. Vrms. So this is what Vrms voltage is required for me to satisfy this condition with respect to this condition. If you not use the Vrms voltage, if you not use this Vrms concept here, then this simply the 5 volt or whatever the AC quantity, whatever the AC quantity you are using here, that cannot be dissipated 1 kilocalorie for a given time t. To meet this point, with respect to this point, so you need to take the RMS value, and that RMS value of this voltage is, if you provide to this AC network, then only for a given time to t it is going to produce 1 kilocalorie of the heat. So that is the importance of RMS value concept when you are going to talk about the AC quantities. Always the AC quantities are measures in RMS, because so this was the reason. So this is what the reason. So that's why we are going to use the RMS quantities for your AC system. So it is you can say RMS value, it is known as, it is known as the effective value or virtual value of the AC current. So that is the, you can, it is a virtual value we are assuming to satisfy these conditions, Then how will you calculate what is the RMS value for a given AC quantity? How will you calculate the, what it means the RMS of a given AC quantity? That is the root mean square of, this is the area under the square by a time period. Area under the square by a time period. So if you take very simple sinusoidal signal here, so this is my voltage signal, and this is again pi, and this is 2 pi. It is I will take only half wave, and I will do the RMS find, because it is a symmetrical waveform. It is symmetrical waveform. I am only going to get only going to take half waveform here. So VRMS I can write here. So this is 0 to pi and it is a root square, so I can write Vm square sine square omega t. So this is nothing but what? This is V is equal to Vm sine omega t. So this equation I'm writing into square by pi and dt. If you solve this equation by using your trigonometrical formulas, so you will get this Vm by root 2. I can take 0.707 Vm. So this is how the average VRMS value or effective value or AC for a AC quantity can be calculated. Now come for the another definition of term is called form factor. Form factor. First you take the definition, then I will explain what is the significance of this form factor. So it is the ratio of RMS value to mean value, mean or that is average value of an alternating quantity, AC quantity you can say. So if you want to write the form factor in mathematical form, then RMS value by mean value, RMS value by a mean value you can write, isn't it? So if what is the significance of this form factor is that it is used to determine the type of waveform, type of the waveform. So that is the significance we are using here. So if you want to calculate what is the form factor for sinusoidal waveform, so what is the RMS value for sine wave? We are getting Vm by root 2. So this is what we have got for RMS value, this one. Then what is the mean value or average value we are getting for this? So this is what we are getting, the average value 2 Vm by pi. I can take this is 2 Vm by pi. So if you do this one, you're going to get 1.11 is the form factor. If you see this index 1.11 is the value in any power system, then you can say that this is related to sinusoidal signal. It is related to the sinusoidal signals. Therefore, the generating waveform, transmitting waveform, and at the utilization at the load end also your waveform is sinusoidal. By seeing this form factor, you can understood that which type of waveform it is. So if it is 1.11 values is coming, then it is a sinusoidal waveform for a given power system. If it is a trapezoidal waveform, then form factor may be different. If it is a triangular waveform, then form factor may be different. So this is how this form factor is going to has significance to find. By seeing this number, you can able to identify whether it is closer to sinusoidal waveform, it is distorting or it is going beyond the sinusoidal waveform. Those kind of analysis you can be easily done, so that you can take some proper precautions to reduce some harmonics in power system, some kind of malfunction in the power system. So that is the significance of form factor. Now comes to that another called this peak factor. A peak or amplitude or crest factor, amplitude or crest factor here. So you can take this, what is meant by this, it is the ratio of maximum value to RMS value of an AC quantity. So this is the peak factor is maximum value by the RMS value. So this is what, if you take the sinusoidal signal, what is the maximum value? Vm. And what is the RMS value for sinusoidal signal? You are getting Vm by root 2. So this is, you are getting root 2, it is 1.414. So this is the value of peak value or peak factor or amplitude factor or crest factor for your sinusoidal signal. Then what is the significance of this peak factor here is, so this is the importance of this one is, importance here is, so this is basically used for insulation and insulation testing and iron losses reduction. It is used for insulation testing and iron losses reduction, you can say, or iron losses assessment or iron losses testing, you can say something. Yeah. So what is this means here? So as we know, the insulation strength is depends on the dielectric strength of the material, and this dielectric strength of the material depends on the maximum peak value, maximum peak voltage, So therefore this peak voltage, you can by seeing this peak factor, you can able to decide what could be the insulation strength and dielectric strength, or some kind of information you can be get from this peak factor. When it comes to how this iron losses testing is, as we know this, in case of transformers, you might be going to study the iron losses. There you have the hysteresis losses is there, and eddy current losses also coming. These are the two iron losses we have. So here hysteresis losses are directly proportional to that flux density. This is the maximum flux density, and it is also directly proportional to square of the flux density, where your flux density are related to magnetization current, and this magnetization current again related to voltage applied. So there, here also you can talk peak value of the voltage, peak value or maximum value of the voltage. So this is how the, if you increase the applied voltage maximum peak value, if you increase, then what could be happening to your losses. This losses test also can be done, and similarly you can do the insulation testing. So these are the significance of this peak factor, form factor, this peak factor, as well as the come to that form factor by seeing this form factor, you can able to differentiate which type of which type of waveform is coming in your power system, or how pure sinusoidal waveform is coming, or is producing in the power system. Those important significant you are able to notice from this terminologies. So with this I will stop this session for today. In the next class we will go into go come up with the fresh topic.